So we've been talking about acids and bases, and sort of specifically last time we finished up sort of talking about salts and what's referred to as hydrolysis. So a reminder that, excuse me, a reminder that really a salt is really generated from an acid and base, right? So when we have an acid and base reaction, typically we make water and a salt. And when we talk about hydrolysis and hydrolysis sort of reactions, we're talking about really the reaction of a salt with water. And a salt really is just an ionic compound. So it is an ionic compound here. And it's really generated from sort of where it comes from as an acid and a base. And, depending on sort of the origin of that salt, what type of acid, what type of base it comes from, will really determine whether or not it will go through hydrolysis. And it really does sort of go back to that sort of relationship that we talked about earlier on in this chapter, which is, if something comes from a strong acid, its sort of partner, which is a conjugate base, is going to be relatively weak. And if something comes from a weak acid, its partner, which is the conjugate base, will be relatively strong. And the same thing basically holds true for our bases as well. So again, if we have a strong base, its partner will be relatively weak as well, which would be like the conjugate acid will be weak. And if we have a weak base, its partner, which is its conjugate acid, will be relatively strong. So depending on sort of where the salts come from, will determine whether or not it will continue to react with basically water. If it does come from something that's sort of strong, which gives us these sort of guys here, these guys here will really produce what we refer to as a neutral salt. So we would expect a salt that sort of comes from this situation here to really end up with a pH of 7 and be neutral in that case. And what that really means is it will not pretty much go and react with water. It will pretty much just hang out there. It won't have an effect on the pH, and thus it's sort of considered to be neutral. Now, if we have a salt that comes from a weak acid, is going to be relatively strong. And in that situation, we would expect hydrolysis to occur here. So because of this, we would expect this hydrolysis reaction to actually occur. And what is the hydrolysis reaction? Well, it's the salt, or part of the salt in some cases, reacting with water. And how will it react in this situation? Well, if it came from a weak acid, the salt would be acting as the conjugate base, and a base, right, is something that will accept an H plus there from the water. And the result of that is it's going to really form hydroxide. And when it forms hydroxide, that means that we would expect this solution to end up being basic with a pH obviously greater than 7 when we calculate it. Same thing occurs if we are dealing with a salt that basically generates from a weak base originally. And in that particular case, we would also have this hydrolysis that would occur. The difference is basically what's going to happen when it reacts with water. So again, we'll have that salt, we'll have that water. And the difference here is it came from a base, which means the salt will act as an acid and it will donate the H plus over. The result of that is we will generate H3O plus. And as a result of that, we would expect the solution to be acidic in that particular case. So sometimes it's important, in sort of salt problems or hydrolysis type problems, they oftentimes don't give you the kind of step before, kind of like where the acid or base that the salt came from. And it's sometimes good to sort of think about where that salt might have originated from. It will oftentimes help you kind of determine, what you should be doing in terms of hydrolysis. There's also a lot of information in the problem, as we talked about last time, that you typically would be given some type of Ka value, Kb value perhaps, and that oftentimes is sort of where the salt comes from, and that you could use that to determine, should I expect it to be basic, should I expect it to be acidic, by doing that reaction. Any questions there on what we talked about last time in terms of salts? All right, so we did one example, I think, at the very end. So why don't we pick up here with this example? And why don't you take a few minutes here, and we're looking for the pH of this solution of sodium cyanide. Given that information, take a few minutes and we'll talk about how you did. First off, we got a salt here, which is the sodium cyanide. And when that is in solution, it will break apart into a sodium ion and a cyanide ion. And the goal here is to figure out, will any of these parts basically go through hydrolysis and react with water? So we talked a lot about it last time. Basically, sodium comes from like sodium hydroxide, for example, which is a strong base, which means this is going to be a neutral salt. Remember, pretty much anybody from group 1 or 2 on the periodic table will not go through hydrolysis, because as we talked about before, groups 1 and 2 on the periodic table is essentially where we find a lot of our strong bases. So this guy is apparently a neutral salt, so we don't have to worry about him. So that really just leaves us the CN minus and whether or not it will go through hydrolysis. And the answer should be yes, it will go through hydrolysis. And how would I know that just looking at it? Well, there is other pieces of information in this problem which is really important. And that piece of information is right about here. So I can find a Ka value here for HCN. HCN is a weak acid. I know it's a weak acid because it has a Ka value. HCN and CN minus are not the same thing, but they are related to each other. That is pretty much where CN minus came from, which means it came from that weak acid. It's going to be a conjugate base that's going to be relatively strong and will react with water. So again, they don't give you sort of where it comes from, but you could pretty accurately probably figure it out. So really this salt was probably generated from a reaction of HCN and sodium hydroxide here. Again, the H and OH would make water, and this sodium and the cyanide would come together to make the salt that we're really starting with. And again, this is a weak acid and a strong base. That is why the sodium part we don't worry about, but the cyanide part we do. So, sometimes it's helpful to look at the information, obviously, that's in the problem. Also helpful to sort of think about where it comes from, as it allows you to understand if it will go through hydrolysis. Any questions on that there? All right, now that we've determined that the CN minus part of our salt will go through hydrolysis, the hydrolysis part of the reaction is pretty, sort of straightforward in the sense of what you're reacting. It's going to be CN minus, and it's always going to react with water in these reactions. Now, the key is, should you give away an H or basically accept an H? In this case, it's pretty obvious the CN minus cannot give an H because it doesn't have one, so it's got to accept an H. But let's just say we weren't sure about that. How could we determine it? Well, again, the CN minus comes from a weak acid, which means the CN minus would technically be its like conjugate base. And when it reacts with water here, it's going to react as a base, which means it's going to accept that H plus. So again, understanding sort of where it comes from also can help you understand what's going to happen when it reacts with water. When it does so, we're going to get their HCN and hydroxide here. And this also always happens in this reaction we produce HCN, which again is where it comes from. So if you're lost as to what you should be writing on that side as one of the products, you also can usually find it in the problem as well. So again, these are things that we talked about last time. You don't want to overlook these sort of pieces of information in the problem that can help you sort of get to your equation. Any questions on that so far? Now, also, as we talked about last time, without even doing the calculation, at this point, we should know that this solution should be basic because we are producing hydroxide here. So again, this is another way we could kind of check our calculation when it's all said and done. We really should end up with a basic pH even before doing it. So initially here, we're just going to do an ice table. We're going to go with 0.75 molar, as obviously this is a 1-to-1 relationship between these two guys. And that is basically how much cyanide we're starting with. We're going to do a 0 and a 0. This is going to be a minus x plus x plus x, which means at equilibrium, 0.75 minus x, x, and x. Any questions on the ice table here? At this point, we're going to go into our K expression, which would be our products divided by our reactants, again, water not included because it is a liquid. And the other important thing about this producing hydroxide and it being basic, we also talked about the idea that you actually need a Kb value here to do this calculation. That's what this is. And very common in these hydrolysis problems, we're given a Ka rather than a Kb or a Kb rather than a Ka value. So that means we do need to use that little formula there, our equation that we talked about the other day as well, which allows us to go from one to the other, and that is Kw that basically does that. So if we need the Kb in this case, it would be the Kw value divided by the Ka, and that would be 1 times 10 to the minus 14, which is Kw's value divided by 6.2 times 10 to the minus 10. And if we do that there, we end up with looks like 1.6 to the minus 5. So we're going to put our values in here. That's going to give us x squared up on top. It's going to give us 0.75 minus x. And again, that's going to equal our Kb value in this case. We're going to assume that x is equal to 0. That will get us x squared divided by 0.75 equals 1.6 times 10 to the minus 5. We're going to multiply the 0.75 to the other side. We're also going to take a little square root action of it. And that is going to give us an x value of roughly, we'll call it 3.5 times 10 to the minus 3. We do want to check it since we did make the assumption. So here we're going to divide it by 0.75, times it by 100%. And in this case, I think we probably should be good. We're like 0.4%. So the check is good here. That means that that is our X value. And in terms of getting to our pH, that also means that that would be our, it would be our hydroxide concentration. So our hydroxide concentration equals X, which equals 3.5 times 10 to the minus 3 molar. That's going to get us not to the pH first, but the pOH. And if we do that, minus the log 3.5 to the minus 3, looks like maybe a 246 on the pOH. Again, in this point, if you for some reason felt this was the pH value, understanding this would also tell you that that's probably not right. So remember, that's the POH. So our pH would then be 14 minus that 2.46. And looks like maybe 1154 would be our pH. I was right here. pH in that case would be 11.54. That does make sense. That is definitely a basic pH in this case. Any questions on any of those sort of steps along the way? So these are hydrolysis problems. In this particular case, we generated hydroxide, so we know it's going to be basic. We can just as easily, obviously, there's acidic ones, as we talked about, where you generate H3O plus. What is the difference in the calculation? There really is no difference in the calculation other than if it was an acidic salt, you would generate H3O plus, which means you would also need to probably swap out the K value into a Ka value. And once you solve for X, the main difference is that would be the H3O plus, and you would just go right into the pH equation and solve for the pH without having to do the POH. But pretty much worked the exact same way. Any questions on salts or how to sort of calculate those pH values?
Professor?
Yeah.
Where did you get the KW like value from?
So that's just the normal KW value for 25 degrees Celsius, which is 1 times 10 to the minus 14. It's essentially a constant, even though technically speaking, as we talked about, it does change with temperature, but that's pretty much a constant number for most problems that you do. And so it's kind of like a constant value of 1 times 10 to the minus 14. And that's just the value of KW. And that comes from what we talked about earlier, which is the KW is the H plus concentration times OH minus concentration equals that 1 times 10 to the minus 14.
Okay, thank you for clearing that up.
You're welcome. Other questions? Okay. So, it's important these salts, and people oftentimes do struggle with a couple of really kind of important things. The first thing is really, writing this equation, and being able to write this equation, as we've been talking about, is really important because, like I said before, I've seen people go with this type of equation and end up somehow with H3O plus and stuff like that. So again, if that's something difficult for you writing these equations, you do want to make sure you kind of practice them and make sure you know how to do them properly, because you could see how it could go really bad for you if you weren't able to write the equation and didn't really understand what you were producing. That if you wrote H3O plus, you would definitely get a different answer, obviously, when it's all said and done. And you probably wouldn't have changed the Ka value as well. So really important to understand, that relationship between those two things. Now, in terms of salts, up until this point, we pretty much have talked about salts where maybe only one part of the salt went through hydrolysis. So for example, in this case, just the CN minus went through hydrolysis. The sodium ion did not. And there is cases where both parts of the salt could actually go through hydrolysis. This is just a prettier picture of what I drew, I think, the other day of aluminum, which is a metal that can also be an acidic salt. And again, here, these are the water molecules basically attached. And again, one of those kind of guys basically get popped off over here to this guy. And again, produces that H3O plus. So remember, that's a kind of another way that you get an acidic salt is through the small, highly positively charged metal. A lot of times a transition metal can kind of do that. But it is possible, though, that more than one part of the salt or both parts of the salt can actually go through hydrolysis. And what that means is, for example, let's say we had something like NH4NO2, right? So if we look at this salt, that is NH4 plus, right? And if we look at this guy, that is NO2 minus. So if we start thinking about where these guys might have came from, NH4 plus probably came from NH3, which is a weak base, which would mean this guy would go through hydrolysis, where he would react with water and act as an acid and donate the H plus over and make H3O plus. But what about our NO2 minus? Our NO2 minus most likely came from HNO2, which is a weak acid, which means it also would go through hydrolysis. When it would go through hydrolysis, it would act as a base and accept the H plus and produce some hydroxide. So now you have a salt here, unlike the ones that we've done before there, that both of them, both parts of the salt could actually go through hydrolysis. So what do? Well, the calculations, if you try to do it sort of longhand calculations with each, are very complicated. So typically what we do in this case is we compare the Ka value of the cation to the Kb value of the anion. And whichever one is sort of larger, that is what we assume would happen. So the Kb value from the anion is greater than the Ka value. We will make the assumption that the solution would be basic. And you pretty much would do the Kb calculation, sort of the basic calculation, which would be like this guy. Now, if you compare the Kb value and it's less than the Ka value, or the Ka value is larger, you would assume that this solution would be acidic. And you would basically do the Ka calculation, which would be that calculation in that particular case. If they happen to be kind of like equal to each other, you probably will have a neutral solution in that case. So in a situation where perhaps you might come across a salt where actually both of them will go through that hydrolysis, what you want to do is really compare the Ka value for the cation versus the Kb value for the anion. And again, whichever one is larger, you would basically do that calculation. Any questions on that? And again, we didn't have to worry about that in the few examples that we did previously, because only one part of the salt would go through hydrolysis. So again, like in the previous example, only the Cn minus went through hydrolysis. The sodium was neutral, so you didn't have to worry about that guy. Any questions on what to do if there's multiple guys going through hydrolysis at once? Okay, then let us talk a little bit about here oxides and acidic oxides and basic oxides and amphoteric oxides. So first off, as we sort of talked about previously, our group 1 here and our group 2 here, this is where we have a lot of our basic oxides. So basic oxides, pretty much maybe with some water, maybe produce something like some sodium hydroxide. It's just a lot of words like sodium hydroxide comes from potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. These are where a lot of bases sort of originate from on the periodic table. Now, our acids kind of come over in our non-metal region of the periodic table for the most part. A lot of those will be over there. And like on the bottom here, we got CO2 plus some water makes some carbonic acid. The arrow's a little bit off there, so we'll just rewrite it here. N2O5 plus some water will make a couple of nitric acids. And so forth. So a lot of acidic oxides, again, that just basically means it's oxygen, happen up here on the kind of upper right there where our nonmetals are placed, and our basic oxides on the left-hand side there. And sort of in this region here, we have some of these amphoteric oxides. Amphoteric, again, meaning that it can pretty much go either way, act as an acid or a base in that particular case. So kind of in general trend, left-hand side of the periodic table, again, your bases, pretty much kind of where they originate from and kind of are generated. Right-hand side and up where our kind of non-metals are, that are oxides, is really sort of where we generate our acids from in this particular case. Any questions on that there? Now, up at this point, we talked about a couple of definitions of an acid and base. And of course, we would want to talk about another sort of definition as well. And we have the Arrhenius definition, which again basically produces H plus in water, or produces hydroxide if we're talking about a base. Bronsted-Lowry definition of an acid is a proton donor, while a Bronsted-Lowry definition of a base is a proton acceptor. So our good friend Lewis felt like he should have some definitions. And if you remembered Lewis of like Lewis structures. So when we think about Lewis structures, we probably think about electrons. And obviously in this case, his definition of an acid and base deals with electrons. So a Lewis acid is a substance that basically can accept a pair of electrons. So it's sort of opposite in the sense of Bronsted, where we talk about an acid donating, and a Lewis acid, it's accepting, and it's also accepting electrons versus protons in this case. A Lewis base is something that can donate a pair of electrons. We definitely will see these guys a little bit later on in the transition metal chapter when we talk about complex ions. But a Lewis base, again, is something that has that ability to sort of donate a pair of electrons. Usually it revolves around something that's kind of polar or has a negative sort of charge associated with it, makes things a good Lewis base. So for example, if we look at H plus and hydroxide here, the OH minus, which has that negative charge, has these pair of electrons that it could donate to the H plus and make water. In this definition here, the acid is the H plus, is going to accept it. What makes something a good Lewis acid? Well, a lot of times if something is positive, right, charged, that means that it lost electrons and is electron deficient. So that makes something a very good sort of Lewis acid a lot of times. So here H plus kind of lost electrons. You're going to be able to accept those, sort of electron deficient, and it will become the Lewis acid and the Lewis base. Same thing if we look at something like NH3. NH3 is ammonia. It's a polar molecule. It's got those non-bonding electron pair. Going to move over to our H plus here again and donate it, becoming the base. H plus becoming the acid. Now, is this different than what you would get if you say looked at the Bronsted-Lowry definition? And the answer is no, it's the same. In the Bronsted-Lowry definition, right, we talk about something donating an H plus and accepting an H plus. So in this case, this guy would be donated over, and he would still be the acid in the Bronsted-Lowry definition. This guy would accept the H plus, and he would still be the base in the Bronsted-Lowry definition. So they do come out the same in the sense of what's the acid and what's the base. But we are talking about two different things. Obviously, one, the electron pairs in the Lewis, and H plus obviously in the Bronsted. Same thing here. Again, this H plus would be donated over, making it the acid in the Bronsted-Lowry definition. NH3 would be accepting that H plus, making it the base in the Bronsted-Lowry definition. So again, they both sort of get you to the same result, but they are looking at different things. What is sort of useful about the Lewis acid base definition is in a situation like we have here on this slide, taking BF3, which is a exception to the octet rule. It's an incomplete octet. It's got less than 8 electrons around it. Less than 8 electrons around it definitely would make it electron deficient and willing to accept a pair of electrons. And that is your basic definition there of a Lewis acid. The NH3 here, just like we saw on the previous slide, having that pair of non-bonding electrons there, able to donate, going to be our Lewis base in this case. And what is so good about this is there's actually no H plus involved here, right? So we can still sort of apply a definition of acid and base to substances here that do not involve an actual transfer of a proton. So that's a little bit more of a general use that you could use in a Lewis acid base sort of definition. Question on Lewis acids and bases. So again, looking at electrons, a Lewis base will donate electrons and a Lewis acid will accept a pair of electrons. Any questions on Lewis acids and bases here? Okay. So we're going to then talk about what happens with polyprotic acids. So polyprotic acids, as we maybe touched upon a little bit earlier on in this chapter, polyprotic acids are acids where we have basically more than one H plus that will come off. So remember, sort of generically speaking, if we're using something like HA, it's going to basically give away an H plus and an A minus, and that is a monoprotic acid. Again, has one H plus to give. H2A is sort of the generic formula for a diprotic acid, will overall give away two H pluses and an A with a -2 charge. And that's the important part there. It has a -2 charge. And again, because there's two of those H pluses, and that's what's referred to as a diprotic acid. H3A will overall give away three H pluses and will have a anion that has a -3 charge overall there to balance it out. And that is what is referred to as a triprotic acid or a polyprotic acid, which is diprotic and polyprotic there and triprotic. So what happens with these H's? Well, as I might have mentioned previously, they do come off basically one at a time. So it is a stepwise sort of dissociation that occurs. All two H's don't come off at once. All three H's don't come off at once. So for example, if we have H3PO4, the first thing that would happen is we would drop off our first H plus, and we would be left with H2PO4 minus. This would have a Ka value for itself, and that step would be a Ka1 value, which we see here in this table. The next thing that would happen is that H2PO4 minus would then drop off an H plus, leaving us an HPO4 2 minus. That also would have a K value associated with it, which would be this Ka2 value. And lastly, what would happen is this guy here would then drop off that third H plus, making it to PO4 3 minus. And that also would have a Ka3 value associated with it. So these come off again, basically one at a time. They have a Ka value associated with each of these sort of steps. So for example, I think this guy there is 7.5 times 10 to the minus 3. This one here, 6.2 times 10 to the minus 8. And 4.8 times 10 to the minus 13, for example. Now, what do we see in terms of what's happening as we try to take off the next H plus and the next one after that? Well, when we look at the Ka values, as you go from Ka1 to Ka2 to Ka3, it gets much, much smaller. And what that means is when we have a small value of K, we mainly have reactants, which in this situation would mean as we go from the first H coming off to the second H coming off, to the third H coming off, and all that good stuff. What we see is it becomes actually harder to do that because we mainly have a small K value. Small K value means we're mainly staying on the reactant side, which means we're not losing a lot of H plus in each of those steps. So if you just think about it sort of logically in that sense, when we lose the first H plus, we now make something that's negatively charged, and you want to get rid of something that's positively charged. So that positive negative attraction going to kind of hold each other there a little bit harder. And then obviously when you remove that second H plus, you got something with a -2 charge. Now you're trying to remove again something that's positive from that -2 charge, and it becomes harder to do. So what we see is generally for all these Ka values, especially on these polyprotic acids, the first Ka value, Ka1 value, is usually larger than the Ka2, and it's larger than the Ka3 value. And you can kind of see that trend going through for everybody here. Now, again, this does happen in a stepwise fashion, although when we think about sort of, this reaction or something, say like phosphoric acid breaking apart, we oftentimes think about it in the overall reaction. And that's why we sometimes think about, oh, all three of them just pop off at once, because when we add together all three of these steps, this cancels, and what we're left with is H3PO4 on the left-hand side of the arrow, and on the right-hand side of the arrow, 1, 2, and 3 H pluses, and PO4, 3 minus. So this is why sometimes, people just focus in on, well, it loses all three. It must all three come off at once, because oftentimes we just look at sort of the overall reaction that's happening, but it does happen in this sort of stepwise fashion, going from one H plus to the next to the next. Any questions on that there? So how does this affect something if we wanted to calculate perhaps the pH of a polyprotic acid, or we want to know what everybody's sort of concentration is in a solution of polyprotic acid? So why don't we go through we'll come back to this here in just a sec. Why don't we look at an example here where we're trying to figure out what is the concentration pretty much of everybody involved. And what is the pH of this solution. So we're going to start with a 5 molar solution of phosphoric acid, and pretty much we want to know everything. We want to know after every step, what is everybody's concentration, what is the pH of the solution, and everything like that. So how would we go about doing that? We have our 3 Ka values given to us here. Again, remember that each of these Ka values represent one H plus that's basically coming off of H3PO4. So we will start with the first step here, and we might as well just go with our very first step here. And our very first step is going to be pretty much just our H3PO4. It's going to dissociate into H plus and PO4, 3 minus. This is basically represented by the Ka1 value that we see over there, and that we also saw on the table, 7.5 times 10 to the minus 3. Our Ka1 expression would be, in this case, the H plus concentration times the PO4, 3 minus. That is not right. I'm sorry. I jumped all the way to the end. Let's try that again. So it is stepwise, so I probably should write it that way, which would be the right way to write it. We actually would end up with H2PO4 minus. Sorry about that. So let me fix that there. Phosphate on my head. There we go. So again, since it does obviously, as we just talked about, come off one at a time, this is what we should get there on the product side. And obviously we would have this guy over here. There we go. And that equals 7.5 times 10 to the minus 3. How do we do this? Well, we do it just like everything else. We do an ice table. So initially we would have 5 molar. This guy here would be 0. This guy here would be 0. And again, we're pretty much just working on the first sort of H plus. It's going to be minus X plus X plus X. And that means at equilibrium, we would have 5 minus X, X, and X in this particular case. First off, any questions on the table? Now that I got the right things written there. Just like we've done before, we're going to take these values, we're going to put it into our K expression here, and we're going to solve for X. So if we do that, that will give us X squared divided by 5 minus X is equal to 7.5 times 10 to the minus 3. I'm going to make my assumption here and assume that X is equal to 0. That will give me X squared divided by 5 is equal to 7.5 times 10 to the minus 3. We're going to multiply the 5 to the other side and take a square root of it. And if we do all that good stuff there, it looks like perhaps we get an X value of, call it, we'll call it 1.94 times 10 to the minus 1. Now we did make an assumption here, so we want to check it. So we will take our X value, which was 1.94 times 10 to the minus 1. We'll divide it by 5, times it by 100. And I'm going to hope it's going to be good. It looks like it is about 3.8%, 3.87%, which means the check is good in this case. So that's good. It didn't have to do any quadratic or anything like that. So what does that mean? Well, based off of our first ice table here, we did figure out a number of sort of answers we were looking for. We know that the concentration of H plus will equal X. So that means it is 1.94 times 10 to the minus 1 molar. So we got that guy. We also see from the table that the concentration of H2PO4 would also equal X, which means it would be 1.94 times 10 to the minus 1 molar. We also see from the table that the concentration of phosphoric acid would equal 5 minus X, and that would get us 5 minus 1.94 to the minus 1, 4.81. Molar in this case, I believe. Any questions on that so far? Okay. So just from doing this first ice table, we were able to get this guy's concentration. We were able to get the H plus concentration, able to get the H2PO4 minus concentrations. Now, we are looking for some others concentrations here. So that's going to make us go into the Ka2 and also the Ka3 sort of value as well. So let us continue on and see how we get to those guys and what's happening. So the next thing that's going to happen is that H2PO4 minus will then lose its second H plus and get us HPO4 minus 2 here. This would be our Ka2 value, which if we peek back is 6.2 to the minus 8. This would be associated with obviously Ka2, which would be our H plus, our HPO4 2 minus, and our H2PO4 minus in this case. So we need to do an ice table. And if we do an ice table here, you might be asking, where does some of these numbers come from? Well, if we go back to our original ice table, that is H2PO4 minus, that equals X. and that would be our initial concentration on the next step. So that was 1.94 to the minus 1. So 1.94 times 10 to the minus 1. Now, what about H plus? Do we have any H plus? Well, if we go back to our table, we actually do have some H plus in the solution at this point. It also equals X. So sort of your equilibrium concentrations from your first table become your initial concentrations on the next table. And that would then get us also 1.94 times 10 to the minus 1. How about HP042 minus? Well, if we go back, it's not there. So this would be 0 in this case. Any questions on that there? Rest of it going to be kind of like normal. We're going to do a minus X there. We're going to do a plus X there. We're going to do a plus X happening there. That is going to get us a 1.94 times 10 to the minus 1 minus X, a 1.94 times 10 to the minus 1 plus X, and an X in this case. Any questions on the ice table here? Okay. Just like we've done before, we're going to now take this and put it into our Ka2 expression over here. And if we do that, we will end up with, up on top, 1.94 times 10 to the minus 1 plus X times X divided by 1.94 times 10 to the minus 1 minus X. And that is going to equal our Ka2 value of 6.2 times 10 to the minus 8. At this point, we had a good luck with the first one. We minus will continue. So we're going to assume X is equal to 0. Again, you cannot get rid of all the X's, but the X's that we're adding to a number, the X's that we're subtracting to a number, those are the X's that you want to get rid of. So if we do that, that will leave us with 1.94 times 10 to the minus 1 times X divided by 1.94 times 10 to the minus 1, and that equals 6.2 times 10 to the minus 8. I think I could do this math. Those are going to cancel out, and that's going to give me an X that is 6.2 times 10 to the minus 8. Just like before, we should check it. So we'll take 6.2 to the minus 8. We'll divide it by 1.94 times 10 to the minus 1, times it by 100. And we're nowhere near 1% at all. So the check is good here. All right. So what does that mean? Well, that means we could see here. I'm on this slide. I do. So we could see here at this point. Actually, we'll put it back on the next page, but I will do it here. A different color here. We could see that the concentration of HPO42 minus equals X, and that means that it equals 6.2 times 10 to the minus 8 molar. So that takes care of that guy. Now, what happened with our H plus and our H2PO4 minus? Well, let's take a look at it. If we take our H2PO4 minus, that is going to be 1.94 times 10 to the minus 1 minus X. And if you do that and you put that into your calculator, 1.94 to the minus 1 minus 6.2 to the minus 8, surprisingly enough, you end up with still 1.94 times 10 to the minus 1 molar. It pretty much did not change from what we had over here, right? That's exactly what we had right there. Now, what happens with our H plus concentration at this point? Well, we take 1.94 times 10 to the minus 1 plus X in this case. And if you do that as well, you end up with 1.94 times 10 to the minus 1 molar as well. It also has not changed very much. Has it changed at all? It has. It changed about this much. But that doesn't make a tremendous difference overall because obviously 0.194 minus 0.00006 is still going to be pretty much the same number. So we do see some change occurring. We see a much smaller change occurring as we try to pull off the second H plus. Any questions on that there? So if we go back to sort of our original question, we now have this guy's answer. That leaves us one last one to go to, which is kind of PO43 minus. And that's going to require us to go to the third step here. So let's do that. So in the third step, what we have going on is HPO4 2 minus going to drop off that third H plus, and now we are going to form phosphate here. That is going to be taken care of by a Ka3 value, which was 4.8 times 10 to the minus 13. The Ka3 expression is going to be H plus PO4 3 minus divided by HPO4 2 minus. All right. So where do we start here? We're going to start with an ice table just like we did previously. And just like we did previously, we're going to get those initial values from our equilibrium values. So we have an equilibrium value here of this guy. And we also obviously have an equilibrium value here of H plus like we did last time. So PO4 2 minus is 6.2 times 10 to the minus 8. Just like previously, we obviously have some H plus still floating around. It actually still has the same concentration of 1.94 times 10 to the minus 1. And we have nothing of this guy obviously there until this point in the process. Rest of it, just like we've been doing, minus x plus x plus x, which means at equilibrium 6.2 times 10 to the minus 8 minus x, 1.94 times 10 to the minus 1 plus x and x. This going to go into our Ka3 expression there. That gives us 1.94 times 10 to the minus 1 plus x times x divided by 6.2 times 10 to the minus 8 minus x equals our Ka3 value of 4.8 times 10 to the minus 13. I've been batting 100 here with my assumption. Should not stop now probably. So let's go with assuming x is equal to 0. Again, going to kill pretty much just the plus x minus x part, not all the x's. That's going to leave me 1.94 times 10 to the minus 1 times x up on top. 6.2 times 10 to the minus 8 on the bottom, going to equal our 4.8 times 10 to the minus 13. Going to multiply the 6.2 to the other side there, and also come back and divide by the 1.94 to the minus 1. That looks like it yields us an x value of 1.5 times 10 to the minus 19. We want to check it. So why don't we just check it with the 1.94 to the minus 1, times it by 100. And again, we're all good on that check as well. Not even 1%. Any questions so far on that? So what does that give us in terms of information? Well, it gives us the concentration of PO43 minus. That equals x, which in this case means it is 1.5 times 10 to the minus 19 molar. Now, what happens again with our H plus concentration and this guy's concentration at equilibrium? Well, we could actually put the numbers in and see. HPO4 2 minus would be 6.2 times 10 to the minus 8 minus x. And if you do that on your calculator, you probably know, but again, if you do it on your calculator, you still end up with 6.2 times 10 to the minus 8 molar, which means, as we can see from the last table, it has not changed. Has it changed at all? It has. It's changed about that much, which is a very, very, very small amount. And if we take our H plus concentration and do the same thing, 1.94 times 10 to the minus 1 plus X, still going to give us 1.94 times 10 to the minus 1 molar. And it's just as we saw before, it has not changed all that much from previously. Any questions on that there? Now, what does that mean if we kind of go back to the original question? Well, we just got the phosphate concentration. So what does that mean? Well, let's talk about what we see here with the actual numbers when we go all the way around. The one last thing that we're looking to calculate is the pH. In order to calculate the pH, you obviously need the H plus concentration, right? So what is our H plus concentration after each of these steps as we go through it? Well, at the very first step, when we lost the first H plus, we ended up with a concentration for H plus of 1.94 times 10 to the minus 1. We then continued on and lost the second H plus. And what did we end up after the second H plus came off? We ended up with the exact same concentration, 1.94 times 10 to the minus 1. Was there any change that occurred? There was change that occurred. It was just a very, very small amount of change that occurred here. We basically added only 6.2 times 10 to the minus 8, which again, with rounding, pretty much means the concentration of H plus remained stable after the first H plus came off, right? So there really was a change that occurred, obviously, but it was so small that it did not make a difference in the overall concentration of H plus after that first H plus came off. What happens when we lost our third H plus? Our H plus concentration at the end also ended up being 1.94 times 10 to the minus 1. Was there a real change that occurred? There was, but that's like, 18 zeros basically, right? So it's a very small amount of change that occurred in that third H plus that came off. The overall concentration of H plus, as you can see by doing this calculation all the way to the end, what we see is where did the majority of all of the H plus come off? In which step did we lose pretty much the majority of the H plus? And that step is the very first step. The very first step, way back here, is where the majority of the H plus would come off in this triprotic acid, polyprotic acid. And why is that? Well, it's for what we talked about. As you lose that H plus, you make something that's more negative. Ka value gets much smaller, which means we're mainly going to, in step number 2 and step number 3, we're mainly going to be staying over here on the reactant side, which means if we're staying on the reactant side in both of those steps, we're not producing a lot of H plus in each of those steps, which is, as we can see here, the change that's happening is very small in step 2 and step 3. So what does this mean about, say, polyprotic acids, and if you had to do some calculations? Well, in general, nothing's 100%, but in most cases, if you have to calculate the pH of a polyprotic acid, and that's really the only thing that you need to do is just calculate the pH of it, you pretty much can almost safely, in most cases, just do the first dissociation, the Ka1 sort of part of this calculation. And that would probably give you the correct H plus value to calculate your pH from. Because technically speaking, at any step along the way here, if I decided to calculate the pH, I'm going to come up with the same because the H plus concentration is the same all the way through, basically. So that happens with pretty much all polyprotic acids. Majority of all H pluses pretty much going to come off in that first step. Does that mean you need to do the entire calculation like we did here? The answer is it depends on the question. The reason technically we would have to do this entire calculation like we did is because in this problem, they wanted to know what the phosphate's concentration was. They also want to know what this guy's concentration was. So the only way to get to those numbers was to do steps number 2 of the dissociation and step number 3 of the dissociation. So sometimes you do come across a polyprotic acid where they, much like this question, want to know what everybody's concentration is. And in those situations, you obviously would have to do each step along the way. If you're just asked really what the pH is or the H plus concentration in a polyprotic acid, you can pretty much safely just do it off of the first step. Any questions on that? With all this talk, we haven't actually calculated the pH in this problem, so let's actually finish the pH here. So now that we know pretty much the pH or the H plus concentration did not change very much along the way, we can go into our pH equation with our H plus concentration, and that will yield us a pH for this guy of looks like 0.71 in this made up example here. And again, that is based off of pretty much the majority of the H plus coming off after that first step. Question on polyprotic acids or how to handle polyprotic acids. Okay. So that should wrap, I think, sort of this little topic here of really acids and bases, salts, and yeah, hydrolysis and polyprotic acids. I'll spit it out. I think I remember what we were talking about. Any questions on any of that stuff there? Okay, so the next thing we're going to talk about that's sort of happening and is related to obviously what we've been talking about here is what happens when we have common ions that occur. So the common ion effect basically will suppress the ionization of a weak acid or a weak base. So what does that really mean? Well, it means that when we have a weak acid or weak base in solution by itself, it will basically break apart, right? And it will break apart into equilibrium. But if we have something else in there with it, it will cause that equilibrium to kind of shift one way or the other. So let's take a common example of, say, let's just take acetic acid, and acetic acid, which is basically vinegar here. And if you have acetic acid in solution all by itself, it is going to break apart into acetate and H plus. Now, by itself in solution, it's going to basically do this. It's going to set up this equilibrium here. Now, what would happen though if we put this same acetic acid in a beaker that contains sodium acetate? Now, sodium acetate is a salt, and a salt, when it goes for a swim, will 100% break apart into sodium ions and acetate ions. And when we look at the sodium acetate and the acetic acid, and again, if we took them both and basically dumped them into this solution, only one thing is going to set up the equilibrium. So it's just going to be the acetic acid here that is going to set up that equilibrium. And when we dump in our sodium acetate into that solution, it's just going to break apart into sodium ions and acetate ions. So when we think about the equilibrium that's being set up in there, it is the acetate ions, right? That is the common ion. So by adding that sodium acetate to that solution, it is effectively like adding more acetate. And what does Le Chatelier's principle tell us? When we add more acetate, it's going to cause the equilibrium to shift to the left. And when it shifts to the left, that means that we will pretty much have more of the acetic acid still together. And what does that mean? It means that it suppresses the ionization of it. When we have more of the acetic acid together, that means, technically speaking, at that point, we will have less H+. Because we have less H+, we would expect the pH to go up a little bit, right? In comparison to if we had acetic acid in there by itself. So if we had acetic acid in there by itself, it would have a certain pH. By having that common ion of the acetate is going to cause Le Chatelier's principle basically to come into play, and it's going to cause a shift in equilibrium to the left, and it's going to basically lower the amount of free H+ that's going to be in that solution, and it will actually have an effect on the pH, as we will see in this chapter. So the presence of common ions basically keep the weak acids together. It keeps the weak bases together because of that common ion that's basically floating around in the solution. Any questions on that? That's what we see there. So why don't we take a look at how we can approach a problem such as this. Why don't you start with just part A for now? Why don't you calculate the pH of a 0.2 molar acetic acid solution, Ka values on the bottom there, and see what you come up with, and then we'll talk about it.